Hi, I'm Rodrigo Obando. I teach computer science at the TCS School of Computer Science at Columbus State University. The name of my talk is Chasing Class Transitions in Rule Space, Cellular Automata Rule Spaces. And the talk is basically about finding the transitions between class behavior and the rule space. Okay, I'm going to start the talk. My name is Rodrigo Bando. I'm with Columbus State University. The title of my talk is Chasing Class Transitions in Cellular Automata Rule Spaces. It's an abstract, and you can actually read that in whatever is going to be posted in Pathable. But basically, the cellular automata has been used since the 1950s when John Boyd Neumann, started with this idea of, investigating artificial life, etc. There was not much research done, on and off throughout the decades until Wolfram started in '83, and he started publishing a lot on that, and there were some other people that continue doing some work on that, and it is used to investigate complex systems, and that is mainly, or not mainly, but it's one of the reasons why it's used, the cellular automata. So what happens with this is that whenever we looked at the rule spaces, how many rules or cellular automata we have given certain parameters, we find that they can be a lot. And then there is what is called the elementary cellular automata, which only has defined two colors and only in one neighbor on each side, and it's a single one-dimensional cellular automata. That actually has just 256 rules. And that is actually, relatively easy to look into because there are not too many. The problem is when you increase either the number of colors or you also increase the number of neighbors that you consider in the evaluation, then those numbers become much, much larger. And in these two examples in here, and now I don't know how to do this. That's strange. Now I have a question. The two fingers not enabled on this notebook? Yeah? It should be. Well, maybe it's not detecting my two fingers. Oh, there you go. There you go. Got it. Sorry. All right. So, for instance, the two colors, one neighbor is 256. And we say, well, let's just use two neighbors, and that goes to 4 billion. And now exploring that particular space is a little bit daunting. And then let's say we say only one neighbor, but we use three colors, and now we go to 7 trillion. And then, so exploring those spaces normally has been simply out of the question. And Santa Fe Institute in New Mexico, where they do complex systems and investigations, et cetera, for a long time, they always just did random searches into the space. So I got interested in this, some time ago, beginning of the 2000s, and I started looking into something like this. So the parametrization of the rules, parametrization, you use that to have an idea of how, to know where those particular rules are. And one of the most known parameterizations is the Limestones Lambda. He proposed that in 1986. And basically, what he said is to identify one of the two states at the non-active state, and then the output of the rule, which is normally a binary number in binary. The number of ones divided by the total number of bits will give you the lambda, and then use that. And the parameter, sort of was useful. And sometimes, depending on how you traverse the space, will give you some meaningful information. It will actually give you places where you would transition in between rule behaviors, et cetera. But then most people, will agree that it doesn't really work as well as he wanted to. Even I've heard that Lantum himself has said that it doesn't really work how I wanted it. So that was, well, one of the problems with that. So what I did is, I published this in, I think it was 2015, a paper where I actually reevaluated the rules. Instead of considering the whole rule, I partitioned the rule into primitives. And if you're interested, I can give you the reference. That's actually published in Complex Systems. And I use something a little bit different from that. And these are just taking parts of the rule. And they're not just split right in half, but there are certain ways to do that. For instance, we call the primitive 0 as the subset of the rule where the central cell is 0. And the primitive 1 is the subset where the central cell is 1. So in this case, you can see, and I'm going to move over there, you'll see that these two and these two are, in fact, this first two and this, what are you? These two are primitive 0, and these 4 are primitive 1. So that's how I divided it, because I was interested in looking at the change in the rule. So whenever there is a change in the state of the cell, instead of just looking at the numbers of ones, which is what Limestones Lambda was proposing, and it didn't really work that well. So what I did with that, for instance, if you look at rule 204 is the identity rule, and there is no change, and that's what the identity rule. Whatever you put into the cells, that's what it outputs for the next step. But rule 51 is the complement rule. What that means, every single bit or every single cell will change to the other state, and then this is the rule plot that display that comes in Mathematica, so that you can see each one of those. So what I found is that I wanted to look at each one of those particular ones, or the ones that actually flip or change the cell. And then I found that I could sort of classify them, and I give them labels. And for instance, if for primitive 0, if both neighbors are 0 and the next step is going to be a 1, that I call it a create, because you have 2 zeros and now you have a 1. And if you have, one on a 0 on the right and 1 on the left, and then you actually change, or 1 on the right, and then it changes to 1, then it's actually a move or a left, and the other one is a right. And whenever you have 2 1s that actually becomes a 1 in the central cell, I call it a merge. And this is just for labeling purposes. So I created a function that that gives me the activity. And in the case of activity 51, 51 is the complement. You can see that it actually contains all those functions. It has the merge, the right, the left, and the create. And also the primitive 1 has the merge, the right, the left, and the create. Whereas 204 has nothing. And it actually makes sense. 204 is supposed to be the identity. It's not supposed to do make any changes. So when I look back in 2004, and that was the second NKS conference, I presented this because I look at those things and I partition them, and I look at that. That's the space of the 256 elementary cellular automata. And these are the Wolfram classes. And you could see that the green, is class 1. The yellow is class 2. The violet is class 3. And this other one is class 4. So I could see that there was a structure in there. And some people told me, well, when you rearrange those things, you can actually get any structure. But I was not just rearranging it because I wanted to make it fit. But still at that time, I had not gone deep into that. In fact, that summer, I went to the NKS summer school, and I started looking into those things. Anyway, and this is where I hope that I'm going to be able to make this one work. I've been fighting with version 12, the differences. And hopefully I will be able to show this. This is supposed to show an updated version of that, that particular view before this one. No, not that one. There you go. It's coming. There you go. So, as you can see here, this is the same, you know, not the same, but it's a rearrangement now of those rules. And we can see that the green on the top ones and the two columns over here, they are symmetrical along the diagonal. They are all class 1. All the blues are class 2, and class 3 are primarily in the middle. And then here we have class 4, the 110, 124, and all the equivalent class, which are in that particular place. Now, when we look at this, and then I look back at Langton's parameter was actually moving from here all the way from this bottom over there. So as it was moving with the parameter, it was actually sampling all kinds of behavior. So one dimension was not enough to really capture that. But when you look at now the number of those functions, you know, the merge, the left, the right, and the create, if you find, you know, these are order using the number of functions, you find in here, and I know that it's very small, but the very top row has no activity on primitive 1. And it doesn't matter what you do in terms of the activity on primitive 0, it's always class 1. It's almost true also for the second row, only for this one here, where you also have not only merge 1, but also have create 0. And that's the only one that it gives you a little bit of, you know, sort of class 2 behavior. But in general, the two top rows or the two columns will give you class 1. So here is where you see where there is a transition in between the different class behaviors. And we find the interesting thing as you move down column by column, when you get to this particular row, it says create 0 is the one that first has some interesting behavior. So as you go down, you actually find class 4 behavior, which is this one here. In class 4, and in this case 110, it has only 3 of those functions. And those, the only thing necessary for that, which is create 1, and it had a move on the sub-0, a merge, and a left. And that's all it needs to actually create the 110 or class 4 behavior. So as we move along, we can actually find class 30 around here, which is, oddly enough, is simply a create 1 with a left 1 and a right 0 with a left 0. And that is all you need to create the class 3 in this case. But as you can see, all the class 3, or most of the class 3, are right in the middle of the space. So whenever you reach certain number of those functions in the rule, all you get mostly is class 2. So what I'm trying to do is to actually go to the bigger space, the 4 billion, and be able to parameterize those other functions, which are actually 16 per primitive, which will then will create 65,535 possible columns and rows. I'm not going to display that. You know, that's 4 billion. I will have to use a very big image to even with 1 pixel, you know, put the behavior on that. But I can explore it. You know, before, because we thought, because of Langton's idea, I believe, I don't know how to prove that we thought that the space or the class behavior was randomly distributed, but it's not. I can see here that we can do these things and see where in the space we find the different classes. So if you put too much activity, there is a point where your class is just going to be class 2. So most interesting activity is if you consider random or class 3, it will be right in the middle. All right, so you could look at this. I have it here just to explore each one of the rows. And if you continue changing, you see it goes class 1. And here you have still class 1. Here you have a little bit of class 2. This is going down on the same one. And then you finally get to this one, and that's what you have a little bit more interesting, which is class 4, class 2, class 3, etc. We can also look at, and I'm not sure if I'm, okay, look at just subsets of those columns and rows, and then you see this actually, when I looked at that, I said, I'm going to look at certain functions like no functions, merge on right, merge on left, merge on right and left, and finally all of them together. And when I put that, on the column, which by the way, those are, if you go back to the Boolean expressions, those are monotone Boolean functions, which the first graphic that I show in 2004 is just that's what I was trying to show, that there is some sort of relationship with the monotone Boolean functions in class 4. It's not totally true, of course, but I could have, I was able to see that before. And this is the complement of that, which is, just flipping it around. Instead of doing that on monotones on the top, you actually do monotones on the column and actually give you the complement of the space. All right, so one of the things that I wanted to do, of course, is go into the 2 to the 32 rule space. And I want to be able to show that it actually continues having that kind of behavior. And let me see if I can make this one a little bit bigger. Unfortunately, this was one of my issues that I had with this new version, so I had to change some things in here. But what this one allows me to do is, first of all, I have a lattice on the left. These rules are on the ECA. These are in the elementary cellular automata. The changes in between this, each one of these is 1 bit in the rule. So the change between this one and this one is just 1 bit. The change between this one and this one is just 1 bit. This one and this one is just 1 bit. So what I do, I have a mouse click function that takes, whenever I say, let's see what happens in between these two. The difference between those two is one bit, but when you project those into the bigger space, the difference between those two is 4 bits. And if I vary those 4 bits now in between those two, I could see, unfortunately you can't see that, but we could see this, and you see how it changes from this particular behavior, which is just solid, to the class 4 behavior over here. And you will be able to see all the phases that it goes through as it changes the different bits into this, which means that this is actually projected into the bigger space and is still showing that they are neighbors in terms of the behavior. So these are not completely, very, very different, which is if it was true that the distribution of the behavior was random, I could probably find some other ones really, really different in between, but I don't. And most of the places that I click on, like this one here, you will see that it just smoothly changes in between. So that indicates, at least this is a peek into the higher space, that they are still continuing with that kind of behavior. So this is sort of a preview into looking into the bigger space. And I wish, as I said, we could actually look at it a little bit closer. Another thing that I had, and let me see if I can just quickly, I know that I'm sort of running out of time. Let me change this in here to a single one. I'm going to initialize all the cellular automata, a single one is the initialization. And it is something that, if you look at most of the displays of the 256 elementary cellular automata, they're just placed from 0 to 255 because there is no reasoning of how put them in any other way. But when you put them this way, and hopefully it will show soon before they kick me out of here, you will see that there is a column, and it's coming. Yes, yes, yes. I like the lollipop. There you go. So if you look at this column over here, you see the Sierpinski behavior, and the same thing you see in the complement, which will go, what are you? Oh, right over here. Oh, no, this is, I just changed the initial conditions, and then it gives me that particular column has the Sierpinski on that. So it shows that there is some correlation. There is something that is meaningful into this reordering. All right, so just to finish up with this, we find that with this parameterization, it gives you a good idea of how to arrange the rules, and that you can see how the similar behavior actually cluster together, and we're able to see where we transition in between those. Well, I can see, for instance, if you have no activity in one of the primitives, your class behavior is going to be class 1. And I actually tried this in somebody else's friend of mine. He's got experiments with class, with k equal to 3 with 3 colors. And I asked him, okay, take this primitive. He actually did it based on the things that we've talked about before. And I said, take this primitive and put no activity on it. And then he tried with the other one. This is the 7 trillion space. And he tried and tried and tried, and all he got was class 1. So that was sort of confirming that. But one of the next steps that I want to do is create a way to explore the bigger spaces to confirm that we can actually, that we have this structure and that it will continue to do that. And I'm thinking perhaps a Packlet with all this, the different functions, et cetera, that I have created, to put them in there. And this will be available in the Pathable. And here's actually the code, that you can run with this an experiment. If you actually do this on a regular notebook, you're actually able to see some of the things a little bit up close. And that's what I wanted to share with you.